All right. It's been a while since I've done a lesson, so let's see how this video recording goes. We're going to talk about ocean acidification today. So, what is ocean acidification? It is when you have a decrease in the pH, so an increase in the acidity of oceans, and this is because they're absorbing atmospheric CO2. This is primarily caused by the fact that there's an increase in CO2 concentrations in the atmosphere. So, if we look at this graph right here, what you're seeing is a reconstruction of atmospheric CO2 concentrations from about 800,000 years ago all the way to a projection up to about 2100. What you'll see is there have been fluctuations in the CO2 concentrations in the atmosphere, and along with that, you'll see measurements of the historic pH of the ocean over the same period of time, as well as a projection up to 2100. What you'll see in this is that most of the time that we have records for the pH of the ocean tends to be slightly alkaline or basic because it is between usually around 8.3 and 8.1. Right now, the pH is about 8.05, and the pH is projected to go all the way down to almost 7.8 if the projections for the amount of atmospheric carbon that we'll have in the atmosphere are correct by the year 2100. So, what happens? What is the link between atmospheric CO2 and oceanic CO2 concentrations? Well, this is a record on this graph of measurements taken in Hawaii of atmospheric CO2. This is the kind of traditional graph that we have seen when we're talking about climate change. And then this measurement at Station Aloha, just north of the Hawaiian Islands, is showing the concentration of CO2 in the ocean. And as that concentration of CO2 rises, you'll notice the pH of the ocean decreases. So, historically, since about the beginning of the Industrial Revolution in the 1800s, the oceans have absorbed approximately a third of the CO2 that's been released based on data, and that's fossil fuel combustion, not consumption. Um, as more CO2 is released into the atmosphere, the oceans absorb more CO2 and then they become more acidic. So, this is going to require us to look into some chemistry. If we look, when CO2 gets dissolved into water, it becomes aqueous CO2 instead of gaseous CO2. That's what this equation is representing. And notice that CO2 reacts with water that's already in the ocean. Notice also that this is a reversible reaction. So if there's more CO2, then the reaction would be driven more this way. If there is less CO2, then the reaction would probably be driven more towards the left. But what ends up being formed is this H2CO3, which is carbonic acid. If you remember anything about acids from chemistry, then you'll remember that acids will dissociate in water and they will release protons or hydrogen ions. That's what's happening here. So you're forming bicarbonate and then you're releasing a hydrogen ion into the ocean, which is going to increase the hydrogen ion concentration, which is going to decrease the pH and make it more acidic. And then that bicarbonate can also dissociate and leave a free carbonate ion as well as more of the hydrogen ions. So notice for every molecule of CO2 that you have going into the atmosphere, going into the ocean, you're going to end up releasing two of these hydrogen ions into the ocean and therefore increase the hydrogen ion concentration, make it more acidic. It's going to become important to keep in mind that we have both bicarbonate, which is this stuff, HCO3, as well as carbonate ions, CO3 released as well, because that's going to become important when we talk about some things later on. So, how do humans influence this? Well, anything that we do that releases CO2 into the atmosphere is going to ultimately increase the concentration of CO2 in the ocean because more is going to dissolve into the ocean. So, anything that traditionally releases CO2 is going to increase oceanic carbon dioxide concentration, so burning fossil fuels, our vehicles, deforestation, any of those. So, what are the impacts of this acidification? Well, marine organisms use carbonate ions, CO3, And they use that to build their exoskeletons and shells because they form calcium carbonate. So they take in calcium ions and these carbonate ions, and they build calcium carbonate exoskeletons if they're things like coral or crustaceans or plankton, or they build shells with them if they're mollusks. So in normal oceanic conditions, or what they were before we had increased levels of CO2, you would have CO2 dissolve in water, it would form carbonic acid. That carbonic acid would form bicarbonate. Bicarbonate in the ocean can then lose another one of these hydrogen ions and become carbonate ions, which will react with calcium in the water to form calcium carbonate, which can then be used to build shells and exoskeletons by these various marine organisms. And that was at a pH of about 8.2. However, when there is ocean acidification, what's going to happen is you're going to release more of these hydrogen ions into the water, which drives this reaction more towards the making bicarbonate side rather than leaving free carbonate. And that means there's going to be reduced calcium carbonate concentrations because there's just not as much of this carbonate. So this carbonate level goes down. Without the carbonate, you can't build calcium carbonate. And then you have thinner shells for your mollusks, you have thinner exoskeletons, and potentially dead coral as well, because there's not calcium carbonate for marine organisms to use. And that's the effect of a lower pH, something like if you had a pH of 7.8. So what effect does this have on coral and organisms that produce these, that have shells and exoskeletons? Well, when they have less calcium carbonate available because there's less carbonate, they have greater difficulty forming exoskeletons. So they will have thinner exoskeletons and be more fragile and more likely to be damaged. Also, as the pH decreases and there's more acidity, the calcium carbonate that's in these organisms' shells and exoskeletons can begin to dissolve into water, making it harder for them to acquire this calcium carbonate because not only is there less of it available, but more of it's being dissolved out of their shells and their skeletons. So this diagram is, or this image is from an experiment where they took shells of organisms and they put them in a pH solution of 7.8, so a highly acidic solution, which is what some estimates are estimating that the pH of the oceans will be by about 2100, the year 2100. And what they saw was rapid deterioration or dissolving of the shells. And that's also because the acid can directly break down the shells of these organisms. Some other impacts are the fact that this can create conditions beyond the range of tolerance. We've talked about the ecological range of tolerance for species. And so when you are outside the range of tolerance for a species, that can cause all sorts of health problems, including decreased immune response, some developmental defects, difficulty reproducing. Another thing is marine algae, especially during algal blooms, can release higher amounts of toxic chemicals when they are in a lower pH environment, which can then poison other organisms and even make its way into humans if they start eating these organisms that have picked up some of these toxins. It also can stunt growth in some organisms, so sea urchins. For some reason, it can cause thicker exoskeleton development in some others, like crabs and lobsters. Some other organisms might not be able to detect predators as well, so they would be easier prey and end up being eaten, reducing their populations. And then there have been some studies that have looked at what are going to be the effects of this lowered pH on various different types of organisms in the ocean. So notice that you have some algae having increased growth, but remember these are also the ones that can release toxins. So that is not necessarily a good thing. You have some diatoms, which are microscopic organisms that live in the ocean that can also have an increase in growth. But algae that require some calcification, meaning they need that calcium carbonate, are going to also decrease in abundance. You're going to have a decrease in the population of clams, scallops, mussels, oysters, all of these various mollusk species, as well as things like squid, cuttlefish, and octopus. So anybody who relies on those organisms for food are going to have decreased food sources. You have sea urchins, sea cucumbers, sea stars are going to decrease in population as well. Also, warm and cold water coral are going to decrease as well in abundance, as well as have less calcification. Some of these crustaceans like shrimps, prawns, crabs, crabs, lobsters aren't going to necessarily have as much of a reaction because they've got a little wider range of tolerance for pH. And then you have various fish species that might end up having a decrease in habitat or food supply, and these effects can kind of cascade up the food chain. There might be some effects on their fitness, though, due to the conditions being outside their range of tolerance. So, what are the impacts on humans? Because we are always concerned about what happens to humans. Right. So some of the impacts on humans are if you have a decline in populations of species, for example, of mollusks, this can also, uh, there can also be disruptions to local food chains or marine food chains that can affect the fishing industry and also reduce food sources for a lot of people in the world who rely on protein products from the ocean in order to be a source of protein. Coral reefs will often have a protective function on shorelines to help protect them from, excessive waves and erosion and hurricanes. So the loss of these reefs can cause increased coastal erosion. This is especially true for island nations, which could reduce the amount of land they have available. So then their populations may have to move further inland, or they may have to relocate to other countries as well. And then without coral reefs, you'll also decrease some ecotourism revenue, which can be a very large moneymaker for some countries. I know Australia, for example, makes a lot of money from people coming to visit the Great Barrier Reef. Then also the toxins that are produced by marine algae could cause sickness in humans, either by being taken up by organisms that humans eat or direct exposure. So all of that is a very big negative, and we'll have some more lessons on some of the terrible things humans do.